I've found my notes. We can resume. So we were in the middle of proving. So remember, A was admissible. So we had this inclusion, and this was the inclusion. And we had this left and this right adjoint. And just before we left, we said that the things that have no Homs from A are the same as the kernel of R, kernel in the sense of what it kills. And perp A was the kernel of L. And maybe the one way to say this is if I'm given some x, some object E in a perp. So one inclusion is easier. Given some E in a perp, then Hom, R Hom from RE to RE is R Hom from I RE to E, because R is the right adjoint of I, and this is 0. So E is 0. And similarly with L. And we wanted to say, so the claim was that if A perp is 0, then A is the whole category. And there's nothing geometric in this. This is all a purely formal kind of thing. So given some E in D of x, we consider the map from the unit of the adjunction gives us a map from E to I. Wait, have I got this backwards? To IR. Which way does the unit of the adjunction go? Oh, sorry. This should be a little e, first of all. Let's see. From. So this is the co-unit. Right, we can see it right there. There's a natural map from RE to RE. And so there's a natural map from IRE to IRE. And let's take the cone. And so I claim that the cone is in a perp. So the cone is 0. So this is a quasi-isomorphism. So IRE is E. So E is in A. Right, so to show that the cone is in a perp, I should take, given some A in A, I want to take Hom from IA and apply it to this triangle. To this So something that we keep saying, but we're not really going to deal with properly until tomorrow, is that not only from cohomology that Hom you get the following long exact sequence. Hom from IA to IRE goes to Hom from IA to E, goes from Hom IA to the cone, and it continues. IA to this is X1, right? And you could go back the other way too. So taking Hom from IA to these things, you get a long exact sequence. So this is plausible, and we'll justify it a little better tomorrow. I guess we should have justified it on Monday or Tuesday, but there was already a lot of abstraction then. And so let's see. Well, Hom from IA to IRE is Hom from A to RIRE, and Hom from IA to E is Hom from A to RIE. So we have a map like this, and so coming from the co-unit of the adjunction, right? It's coming from the co-unit of the adjunction here. And if you read Saunders-MacLean and you really like units and co-units of the adjunction, you know, wait, something's wrong. This I should not be here. You know that the map, right? How do the unit and co-unit of an adjunction go, right? You have the unit, the co-unit like that, and you have the unit like this. And the map are these backwards? Yes, they are backwards. Thank you. There's a lot of left and right to mess up here. This should be epsilon, and this should be eta. Thank you. Right, so there are, and you can do that, well, you can compose them. If I go from R to RIR and back, here via R times epsilon, and here via eta times R. Then this composition is the identity. Well, so by the way, I'm claiming that, where am I going before I use that? I'm claiming that this map is an isomorphism, and therefore all these maps are isomorphisms, and therefore all of these are 0, which is exactly what I wanted to get. I'm saying that the cone is in A perp, so it's 0, and so we win. So what does it mean to be in A perp? That means that there are no x's whatsoever from anything in A to the cone. So I want all these to go away. So I want all those to be isomorphisms, and that's what I'm arguing. Right. So the general adjoint functor business tells you that this map is induced by, so this should have been an epsilon, shouldn't it? So this is given by an R epsilon. So MacLane will tell you that this composition is always the identity. And what I claim is that because I is fully faithful, I is the inclusion of a subcategory, I is fully faithful if and only if the unit of the adjunction, eta, is an isomorphism. Right. So this is an isomorphism. And that was an isomorphism, so that's an isomorphism. Right, so why is this? Right, the map from Hom AA in A to Hom IA in D of X. Fully faithful means that this map is an isomorphism. And this is Hom in A again from A to RIA. Or sorry, I should maybe call this one A prime or something. So this map is the one given, it's induced by eta right there. Right, and MacLane will tell you that this map commutes. So by the Yoneda theorem, right, saying that this map is an isomorphism is the same as saying that the map induced by eta like this is an isomorphism. So by Yoneda, it's saying that the map, this is true for all A and all A prime. So it says that this map is an isomorphism for all A prime. Like, yeah, even that's a very MacLane kind of fact, right? That your functor is fully faithful if and only if the unit of the adjunction is an isomorphism. So now once we show that the subcategory, yeah, how have we been using this? We've been saying we have some subcategory generated by an exceptional collection. Its orthogonal is 0, and therefore it's the whole thing. So we need to say that the subcategory generated by an exceptional collection is an admissible subcategory. But while I'm here, this this cone of the identity, where did it go? This cone of IR to the identity, which it's not obvious that that's a functor. It's obvious that it's well defined on every object, but it's not so obvious that a map between objects gives you a maps. That's something special. But I claim it is a functor. And this projects from from D of X into A perp. And similarly, cone of 1 to IL goes from D of X into perp A. And actually, we've already seen So if you believe that that's a functor, then you can see that it takes, we've just seen that it takes values in that orthogonal. So this is moving towards the fact that if A is admissible, then its left adjoint, or its left orthogonal is admissible, and its right orthogonal is admissible. I think I might leave some of that to Sasha, but this is heading that way. I claim that we've already seen this kind of map once before when we were doing those mutations with the plane on the quadric. So notice if E is exceptional, then the functor from the derived category of K vector spaces, we're over a field today, to the derived category of X, which just sends V dot to E tensor V dot. This functor is fully faithful. Right, so E, well, you can see it, right, but I want to think of this, by the way, as the derived category of a point. Right, so earlier we said if you have a fully faithful functor from the derived category of one space to another, then the image is an admissible subcategory. And how, well, if I think of E as an object on the derived category of a point times X, then the Fourier-Mukai functor induced by E from D of a point to D of X is the functor above, right? This functor. You're just taking a complex of vector spaces, pulling it up to this product, tensoring it with E, and pushing forward to X. And in fact, it's you can see, so yeah. So K goes to E. This had the X algebra here is just K. That's maybe the silliest thing you could say. And the X algebra on X of E with itself is K because it's an exceptional object. And this map is an isomorphism. So in fact, E is exceptional if and only if this functor is, for any object in the derived category you can think of as a functor from the derived category of a point to X. And that functor is fully faithful if and only if the object was exceptional. Should I write that? Maybe I should write that. So objects d of x are the same as functors you just ask where, this way you ask where oval point goes, And then because everything here is a sum of your basic O of a point, then that tells you where they have to go over here. On the other hand, every functor like this gives you a map that way. This is sort of a trivial observation, but it's nice to make. And exceptional corresponds to fully faithful. Where was I going with that? So what is the left adjoint? Right. So if I have this functor from the derived category of a point to the derived category of x, which sends v to the tensor E, then the adjoint of the left adjoint, so that was my fully faithful functor if E is exceptional. The left adjoint sends some f to R hom from E to F. Sorry, I'm suddenly worried that I'd written this. Is that the left adjoint or the right adjoint? No, this is the right adjoint, isn't it? Yeah. Hom help me out. Is this left ad? Yeah, if I do hom from V tensor E with F, this is hom from E to, from V to R hom of E F. Right, so this is the right edge. Okay, good. And the unit of the adjunction from 1 to Ri, well, Ri is just, this is just talking about hom from E to, R hom from E to itself. Well, is tensoring with that. So that's tensoring with K. So if E is exceptional, then indeed this unit of the adjunction is an isomorphism. Sorry, I belabored that a little bit. The point I'm trying to make, and only barely succeeding, is that if E is exceptional, and F in D of X is arbitrary, then we can take this map R hom EF tensor E to F. We can take some evaluation map here, and we can take a cone. And we've done this before, right? So for example, we took R hom between OQ and this ideal sheaf twisted by 1, tensor OQ, and we took the evaluation map to I, and then the cone was actually this kernel, the spinner sheaf, but we said the cone is a mix of kernel and co-kernel. So there was no co-kernel, so we only saw the kernel part of it, and we were playing with that. But this was just K3 in the example that we studied earlier. So, but I claim in this new, much more categorical, so this sort of reasonable geometric thing that we did when we were playing with explicit examples has this categorical incarnation. Right? IRF, when I is this and R is that, is exactly R hom EF tensor E. And the map from there to F is the evaluation. Sorry, I think anyone who hasn't seen this before is sufficiently pissed off right now. So the point I was trying to make is when we were in a categorical setting, we were using this kind of cone to project into the orthogonal to A and then mess around. But earlier when we were in an explicit example, we used this construction to project into the orthogonal to O, and it was the same. It's secretly the same, but now you see. Maybe you see. Sasha will talk more about this when he comes to this kind of thing. So, all right. If you fell off the horse, maybe now's a time to get back on. So we have this definition of an admissible subcategory, so where the inclusion had left and right adjoints. So our examples were the image of a fully faithful embedding from d of y into d of x. And in particular, the subcategory spanned by an exceptional object, because that was a fully faithful functor from. So if E is exceptional, because that was a fully faithful functor from a point, and soon we'll also say. Either today or next week, the span of an exceptional collection. Sorry, the thing generated by an exceptional collection. And our non-examples were things like the thing generated by skyscraper sheaves. And the way we knew this wasn't admissible is because its orthogonal is 0, and yet it's not the whole category. And here's another one. Since we've seen a lot of blow-ups of surfaces or whatever at smooth points, here's another one. If I take a surface with an A1 singularity, with a node, and I blow up the point, if I blow up the node to get sort of, well, I'm never quite sure how I want to draw that. So I'm blowing up that point, and I have some exceptional curve here. But now the normal bundle to E in x tilde, if this is x and this is x tilde, is now O of minus 2, not O of minus 1 anymore. You can use Serre duality and the fact that the normal bundle is the canonical bundle. Right? E is still a P1, right? But now it's a conic rather than a straight line. You can use Serre duality to check that OE left orthogonal is the same as its right orthogonal. And that will imply soon that, that the subcategory generated by OE is not admissible. And just to say the words OE is rather than an exceptional object, it's a spherical object. So the Ext algebra of OE with itself is K, 0, and K. So I'll return to this in a second and explain that a little more clearly. So a semi-orthogonal decomposition is a sequence of admissible subcategories A1, A2, up to AN in D of X. It's going to be just like an exceptional collection. Such that, let's say, AJ is orthogonal to AI whenever I is less than J. So there are no Homs from right to left, just as before. So if you prefer, we can say that AI is contained in AJ perp, or AJ is contained in perp AI. If you like that. And they generate D of X. So this is like a full exceptional collection. Only instead of having all our things be generated by single objects, they could be bigger than that. So I want to give two examples, and which are a PN bundle and a blowup, and then I want to explain why we want a semi-orthogonal decomposition and not a fully orthogonal decomposition. And then I have a feeling that we'll use up the hour. So example. So let E be a vector bundle on X, and P be the projectivization of E, which is going to map to X, and I'm going to call that map pi. I'll call it F, because in the exercises it's F. Then the functors F upper star from D of X to D of P is fully faithful. And similarly, the functor that's you pull something back and then tensor with the relative O of t for all t. So relative O of t is a line bundle up here, which is O of 1 on all the fibers. And the derived category of P, this is some family version of Bailenson theorem. It splits as f upper star d of x, f upper star d of x, tensor OF of 1 up to f star d of x, tensor OF of n. Well, I should say, so this means, this notation with these brackets means this is a semi-orthogonal decomposition. N, yes. So the rank of E is going to be n plus 1. So F is a Pn bundle. Thank you. Right, so what do we need to show? We need to show that that functor is fully faithful. We need to show that there are no R-HOMs from right to left, and we need to generate all the points. And I think I'll leave to Sasha that if you have that the span of any finite subset of these things is a if you take two of these things, what they generate is again admissible. I think I don't have time for that, but it's basic. It's like a fundamental thing. Okay, so why is F upper star is fully faithful? Given some OA and B in the derived category of X, R-HOM from F upper star A to F upper star B is R-HOM from A by adjunction to F lower star F upper star B. Which is R-HOM from A to B tensor F lower star OP by the projection formula. So this was by the projection formula. And F lower star OP is just OX. So this is a flat thing, and you know the cohomology of O on the fibers is what it should be. So by Grauert. Oh, I'm sure someone's going to ask how this doesn't look like the projection formula that you've seen, right? But you use it this way. I rewrite F star B as F star B tensor OP, and then this is B tensor F star OP. So this is like that. So that gives that this is fully faithful. I guess really we should say that the natural map gives you an isomorphism, and that amounts to saying that the natural map from OX to this thing is an isomorphism. and that's true. Next, I want to show that there are no R-HOMs from the later ones to the earlier ones. This is going to be a lot like Bailenson. Well, it's going to be a bit like Bailenson. So given A and B again in D of x, R-HOM from F upper star A twisted by I to F upper star B twisted by J So how many steps shall I do at once? First, I can put this over here and turn it into O of J minus I, and then I can move the F upper star over to become an F lower star. I'll write that as A F lower star of F upper star B tensor OF of J minus I. By the projection formula, this is B tensor F lower star OF of J minus I. So now I'm taking cohomology along the fibers of, well, this is 0 if this same condition. If well, for our i's and j's. Right, if we're going from right to left, then J minus I is negative, but not too negative. So this is just a family version of what we did earlier with Bailenson. And then why do they generate? So given a point P in P, right? So here's X, here's P, and it's a Pn bundle. And if I've given some point there, I can, let's let, what shall I call that fiber? Okay, I don't want to call it F, that seems bad. Let Y is F inverse of F of P, which is a Pn. Right, and then, right, so Y is F upper star O F of P. So that's, and we can generate, we have this, right, we have OY goes to OY of 1 to the n and so on to OY of n. We have this Koszul complex that gives us OP. Koszul complex on that PN fiber. Oh, yeah, sorry. OY. Thank you. Right, so I have all the points downstairs, and so I can get, from here I can get O of all the fibers twisted by 1 twisted by 2, O of all the fibers twisted by n. And from that, I can generate all the points in the fibers. Okay, so that, that generalized the Bailenson story from a single PN to a PN bundle. And if you're into Brouwer groups, you know that there are PN bundles that are not the projectivization of a vector bundle. And Bernardara has a little generalization of this, where the derived category of the total space decomposes into the derived category of the base, and then the base twisted by the Brouwer class that obstructs whatever, and then twisted by the Brouwer class squared up to whatever the right number is, if you like that kind of thing. So let's talk about blobs. All right, so if I have some z and x and they're both smooth, and x tilde is going to be the blow up along z of x. Let's call this inclusion I. Let's call this F. Over Z, I have this exceptional divisor. Maybe I'll call this G and this J. As big as it needs to be. Anything you like. So let's call it codimension in X. Let's call that K for codimension. Right, so we're going to generalize what we did with the blowup of P2. We're going to generalize it pretty severely. So, so first of all, I want to point out that F lower star of OX tilde is OX. You can use the same proof that we used before. And so F upper star is fully faithful. I think I just erased the argument for why that was true. No, it's here. Right? Same reason. If the push forward, if the push down of O is O, then the pullback is fully faithful because you just use the projection formula. I'll leave that there for a minute. But we saw before we had, when we were blowing up P2 at a point, we had a bunch of things that came from the base. We just had a copy of the exceptional collection from the base had been pulled up. And then we had something that was supported on the exceptional divisors. So here's, moreover, the functor from d of z to d of x tilde, given by maybe f goes, I'm going to pull it up. I'm going to tensor it with OE of TE for some integer t. Right, which is OE of E, this is the O of E over Z of minus T, right? Because remember this G, this is a PK minus 1 bundle. It's the projectivization of the normal bundle of Z. And then I'm going to include. This is fully faithful. I think I actually want to prove this in this case. I think it would take me another half an hour to do it sort of at a speed that you can, that everyone can follow. So, but I do want to point out it's very similar. Well, I'll point out at the end it's the same as what we did when Z was a point and X was a surface, just including line, you know, if Z is a point, I only need to think about O of that point, and then I pull up and I include E. It's a similar calculation, only fancier. Right? I mean, how will you show that this is fully faithful? You'll compose with its right adjoint and hope that you get back the identity, right? And the right adjoint is going to involve some J upper shriek, and then some some tensoring with the opposite line bundle, and then some G lower star. And well, J upper shriek, J lower star takes, it's a little bit fiddly. But it's not just the identity, but it also picks up another copy of O of E. Right, so that's the piece of work that I'm avoiding doing. But then when you push down with G lower star, then it kills that second piece that you didn't want, and you're back to the identity. Let me not. Yes. Yes. So this is a Fourier-Mukai transform. Some Fourier-Mukai transforms are fully faithful, some are not. Yeah. I mean, well, some people use, yeah, no, it's not true that every functor given by a kernel is fully faithful. I mean, essentially every functor that you care about is given by a kernel, and so some of them are not fully faithful. Yeah, no, it's okay. Yeah. For example, we said that every object gives you a Fourier-Mukai functor from a point, and that functor is fully faithful if and only if the object was exceptional. So any non-exceptional object. Right, and then the statement, this is another one of Bondel and Orlov, is that I should give this functor a name. Let me call this phi sub t. D of x tilde is, over here I'm going to have just f upper star of d of x, and then I'm going to have phi 1 of d of z, and phi 2 of d of z, up to phi k minus 1 of d of z. So the claim is there are no hums from right to left. So each of these is a fully faithful functor. So it gives me it embeds a full subcategory, and that inclusion has left and right adjoints because they were built in geometric ways. But the claim is that there are no hums from right to left, and that you can generate everything in x tilde in this way. Oh. Thank you. Phi is this thing up here. That, yeah, that, here was Z. Right, so E is fibered in projective spaces. So you take something on Z, you pull it up, you twist by whatever line bundle on the fibers that you need to, and then you include. And you should compare, by the way, that the cohomology of hi of x tilde z is pullback of the cohomology of x, z, plus the sum from j equals 1 up to, or up from 0, well, plus copies of the cohomology of h of z. Let me not try to get all the indices right, but it's exactly the same thing. You pull up, you cup with the hyperplane class on E, you push forward. So by a very similar formula. Let me finish today by just saying for the blow up, do you see how for the blow up of P2 at a point, so if this was D of P2, this is giving you your O of H, and O of 2H. And these are giving this OE of minus 1. There's only one of them, right? And Z is a point, and we're just talking about one object. Okay. I had more to say, but then I rambled about units and co-units, which somehow there's always, whenever you start talking about units and co-units, that's the way it goes. All right. Thanks.